Hello everyone! My goodness, we have been experiencing a rough ride in the last days. I hope you can all hear me, and I'm just going to jump over and introduce myself and just explain what's been going on. We've had a lot of wind. It was quite incredible. First we've had terrible weather, then wind. And this is one thing you have with astronomy. You need lots and lots and lots of patience. Okay, so patience is really important. I'm just going to open my live chat here. 1 second. And yeah, do type in some comments. So I hope you can hear me now. All that I should be live and everything should be fine. So I'm going to just show you a little bit through some of the logistics, so that I think the logistics have come a bit short in the last days, because it's not so clear where you do certain things. So I'm just going to walk you through this now. So let's have a look. I'm going to jump the screen now. And you can see here, that's actually the live window that we have. That's like the cockpit. And from there, okay, very good. You can hear me loud and clear. That's good. So this is the cockpit that we have. And you can see we have weather information, everything. I just want to walk you a little bit through our logistics first. But in the meantime, before anything happens, I'm going to just start the first image. And you can see we're going to focus on two great objects today, and it's going to be super exciting. I've been so excited to show this to you, and unfortunately we haven't had much luck, so I'm going to acquire the first image whilst I talk, and there we go. So that's running, that's good, that's a big telescope, and I will explain to you shortly what we're up to. But I just want to walk you a little bit through the logistics. Okay, so let's see here. Okay, so first of all, you saw, for those of you who saw the first episode, we have put lots and lots of comments underneath. So if you scroll underneath the first episode, you will find everything you need. It's a little bit of an explanation what we did. You'll find the notes, the links to the notes, and we'll put the links for the images, and if there are any notes to be downloaded, we'll probably put them a few hours afterwards underneath each episode. Okay, so there's a link for you. It'll be a link everywhere. So if you go back to episode 1, you'll find this. Also, the information about sky tours is there. The way you can subscribe. All the necessary links are there. And then what is also not clear, and I completely understand that, is how to comment. Okay, so I'm going to just jump to another window, and let's assume you're new. And by the way, thank you so much, Franz Gruber and Matthew, for your kind comments. Your comments are really welcome, and usually you find the comment page on the on the right hand side, but it's a little bit confusing if you haven't used YouTube before. So for example, if you wanted to comment now and you were not registered, if I click on here, you can see I come to my accounts. Which account do you want? So let's assume you have no account whatsoever. Then I would say add account here, and then you enter your email to sign into YouTube. But if you do not even have that, you can create an account. So everything is in YouTube, although it seems a little bit complex. You have to be registered as a subscriber in order to comment. But it walks you through everything, okay? That's the good news. It walks you through everything. So you put in your name, everything you need to know, and it walks you right through. And just in case, 1 second, I'm just going to jump back. I've also put the same information just below there. There's another video that says, in order to comment an episode, you need to have a YouTube account. This is how to do it, and there are lots of very helpful links. It just is the same, basically, what I just explained to you. So much for the logistics. I hope that helps. So then you can also see live stream starting soon, the Sky Tours pages here. So if I click on here, you can see that. And then we should actually be seeing, yes, we can see exactly what I'm doing here live. So all that is fine. And that's so much for logistics. It is really, really important for us here at iTelescope that this whole episode is interactive. We want you to participate. It's education and it's a lot of fun. That's why I'm here. I love fun. I love the sky, especially the southern sky, and I want you to enjoy it. So that's, I hope that helps you. There's also the link to the iTelescope Sky Tours. Please subscribe to it. It's all part of that, okay? And here's our live episode, by the way. Then, talking about weather. Everything is weather. So, you can see here the status. At the moment, I wonder if this is a live one. Is the roof closed again? I'm not sure. Just have to refresh the page. Let's see. No, the roof is open. You can see the roof is open indeed. So this refreshes and you can see we have high winds, and this has been causing us a lot of pain. Of course, I want to run as many sessions with you as possible, but because they are scheduled, and I'm scheduling according to your convenience at North American time, so it's 8 a.m. Pacific time, 11 a.m. Eastern time, and also in Europe, it is about 5 p.m. For France, Germany, and so on. And then it is about 4 p.m. for the UK. So this seems to be a very good time slot for everyone. Of course, there are also people in Eastern Europe, and then they're 12 hours different. But we think that we can accommodate most people this way. That's why we except our Australian friends who have to unfortunately do this at 3 a.m. in the morning. Okay, so we can't get it right everywhere, but the weather does play an important role. So what have we got today? I just am so excited to show this to you. So let's just get back. Okay, so I can see your comments. So don't hesitate to put in any comments. I know it's been a lot of delays, but we've got two great targets today, and these are really absolute marvels of the southern sky. We've got first Omega Centauri. Omega Centauri is the biggest globular cluster in the southern sky. It is an absolute marvel. There is nothing like that in the northern sky. And then there's also the Eta Carina nebula. It's another incredible marvel with a crazy star. And that's what we're going to talk about, okay? So let's travel first to Omega Centauri. So Omega Centauri. What is Omega Centauri? Omega Centauri is, as I just mentioned, a globular cluster. What's interesting about globular clusters, and I'm going to explain a little bit just as we are acquiring the image, a globular cluster is basically a bunch of stars packed tightly together in a sphere, and they are believed, not only believed, but they are known to be the oldest stars in the universe. They're older probably than our own galaxy. They evolved just after the universe was rapidly expanding and galaxies were formed. So it is very, very likely that these globular clusters, and they consist of really, really old stars, 10 billion years and older, are the essence to study if you want to understand the evolution of the universe. And we're going to look at an amazing globular cluster here in the constellation of Centaurus at a distance of approximately 15,000 light years. Now, if you go into literature, you'll find sometimes they say 15,000, 16,000, 17,000. That is the accuracy that one has, maybe around 10-20%. Okay, but there are deviations in this. Okay, so don't unless someone has really traveled there or has done some very accurate parallax measurements. These measurements do have certain uncertainties. Okay, so let me just jump back to our live screen here and see what the system status is, where our telescope is at the moment. Image is being taken, so very good. It's exposing, very good. And let's just jump back again. Here we go. There we go. And this is the marvelous southern sky. This is the Milky Way as you typically see it in August. So I just wanted to show you what's interesting about globular clusters. This is just as it is taking the image now of this fantastic globular cluster. What is so incredible about globular clusters is they are all around the halo of the center of the Milky Way. Okay, so what we're looking here, right, that bright spot in the upper middle, that is Sagittarius. Sagittarius is beautifully visible from the southern sky. We can also see it from the northern sky, but it's lower. From Hawaii, they have a very good view. And by the way, Sagittarius, because it is the center of our galaxy, has been extensively studied, especially with radio telescopes, with X-rays, and with many others. So it is very interesting. And what is interesting about globular clusters is there was a very famous astronomer in 1917. Here his name was Shapley, and he studied a certain type of stars called Cepheids. Now Cepheids are variable stars. They are like lighthouses. They tell you something about the distance, and we will spend much more time about classification of stars in later sessions. But he was able, through their brightness, able to calculate their distance. And he noticed that if this is the galactic plane, this dust layer, around the halo, which is a big halo in the center, all the globular clusters seem to be evenly distributed there, but not quite evenly, because what he did, and this is quite a beautiful picture, he mapped out, and there are about 150 globular clusters, and he did all this marvelous work in 1917, because at that time or before it was still believed that the sun was at the center of the universe, okay? I mean, he wasn't sure where we were, even in our own galaxy, but what he did is he mapped out all these globular clusters because he assumed that they were evenly distributed around the center of our galaxy. And when you look at the picture, you can see in the middle is our sun, and you can see it looks asymmetrical. Something doesn't look symmetrical. So what he then did cleverly is he rearranged the whole picture. And now you can see our sun. Actually, if you look at the lower, let me get my arrow. Sorry, I need an arrow. I needed my arrow here. There we go. There's my arrow. That's much better. That's where the sun is. You see that? That's where the sun is. You rearrange everything by globular clusters. This was an amazing discovery, because that way he could map out that the center of our own galaxy is indeed Sagittarius, and it looked all symmetrical by just rearranging everything. And the problem was solved. So beautiful, beautiful work. And suddenly we knew where we are in our own galaxy, which is an incredible, really incredible advance in astronomy. So let's just see. We have, the script has ended. So I'm just going to take you back to this beautiful, let me just get rid of my arrow here, and let's just preview the image. 1 second. So click here, let's do it. Wait a second. Oh my goodness. And this is absolutely magnificent. This is a globular cluster of its greatest beauty that you can imagine. You are looking here at about 10 million stars. It's absolutely incredible. 10 million stars, very old stars. And Omega Centauri can be seen, you can see it as a fudge, just as I showed you before. If you look back on the Milky Way, you see that, let me get my arrow quickly and show it to you. There, that's where Omega Centauri is, right there. Okay, that's where Omega Centauri is. Now, before I forget this, let me quickly launch the second telescope, and then I'll go on explaining, because we have to do so much in parallel in order to get everything done in a very short time. So I'm going to launch several telescopes now on the Eta Carina. 1 second, where are we here? Single image. There we go. That's a single image. 1 second. Let's go back here. Where is my single image? Oops, not sure. There we are. Okay. So we got Omega Centauri here. We need, one second, we need another one. We need, I don't know what happened to my Eta Carina now, one second. Oops. Let me just type in Eta Carina quickly. Eta Carina. And say get coordinates. There we go. And we are going to take, and I'll explain this to you in a moment why we're doing this. But I'm changing the settings now. And I'm going to acquire this image. Should be working. And I will also, yeah, there it works. And I will do the same with two other telescopes. Take a wider map, in fact. So we're going to acquire the image on this one, and then I'll go explain that, what I'm actually doing. And also on another telescope, so we're really utilizing the telescopes very well. It's much more fun this way. So we've got 3 telescopes looking at our next object. And I'm going to just jump back to our beautiful Omega Centauri. There we go. That's our beautiful Omega Centauri. The only difference that you see here, now this is in color. This is all in glorious color. Okay, so this is actually what Omega Centauri looks like when you do all the fine colors. So it consists of 10 million stars. And what is so interesting about it is you can ask yourself, well, how would it be if you lived in the middle of this incredible cluster? I mean, how dense is such a cluster, and what would it look like, right? I mean, could it be possible that we would have life inside such a cluster? Maybe we would have been in such a cluster instead of our galaxy, and what would it actually appear like? And this is the interesting thing. Globular clusters are crazy dense, and there were 2, I think they were Canadian astronomers who did some beautiful work that I just wanted to show you, because they actually sat down and said, well, let's put a hypothetical Earth inside this cluster. And so they didn't use Omega Centauri, they used another cluster, but it's more or less the same picture. And they calculated that the closest star is about 0.05 light years away. Now, our closest star, as I showed in episode 1, is about 4 light years away. And this one is 0.05 light years away. So they built this hypothetical picture. And it is interesting because usually in our night sky, we have about 29 stars of magnitude 1. Those are the bright stars like Sirius and so on. Okay, we have about 29 of them. But in this case, you would have 10,000 very bright stars. 10,000, imagine that. And it would be so luminous that the cluster's sum would combine to an average sky brightness about 20 times brighter than the full moon. Okay, so there you go. That is I think that's rather interesting work because, apart from the question whether there could be any planetary systems in globular star clusters, it does give you something about how luminous they are. Now, there are a lot of collisions also that you have in globular clusters, and open clusters are even more crazy, and we're going to see some of these, okay? So what's interesting, again, just to summarize, what we've learned from globular clusters today is they helped Shapley in 1917 to identify where we are in our own galaxy. So he was able to map it out by assuming that they're spherically distributed around the halo, which would be the center of our galaxy. And we quickly found out we don't live in the center. We live on a spiral arm out on the Orion or near the Perseus arm. Okay, so that was an interesting discovery. And then the other thing that we learned, there are about 150 globular clusters, the brightest one of which is Omega Centauri, absolutely marvelous, containing about 10 million stars, far more than any of the other ones. It is, as far as we can tell, the brightest globular and the finest globular cluster we have. They are much older than our own galaxy, and there are still a lot of mysteries. They do know that the age of the stars are very, very old. They look at the spectrum of single star. That means the light that comes from, and they dissect the light into colors, and they thereby know what the ages of the stars are. And they know that they are sort of a self-contained system where you have stars that are old, that are towards the center or the core of a globular cluster, and then you have a second generation of stars there too, and that basically happens when a star explodes. For example, it dies as a supernova, so it then the gas and the ejected mass is recycled and new stars are born. So you could see it's basically a self-contained living system inside a galaxy, because globular clusters are rotating around our center. So quite interesting objects, old, incredibly dense, and very, very bright. Okay, so that's what we've learned. Now let's jump back and let's see what our telescopes are doing, because it's going to get even more exciting now. So let me just see what the system status is. Ah, they are still working away. So yes, let me explain the next object. Okay, let's jump back. Let's jump right back. So here again, you see our Milky Way in the south, okay? And Eta Carina is interesting. It's very, very close to the Southern Cross. It's south of the Southern Cross. So it's the Southern Cross is, let me just give you the arrow again, and let's hope by the way, last time I had a system crash. Sorry about that. If I suddenly disappear, you know, nothing is perfect. I'm doing all this from my home. Internet seems to be better, but sometimes the system crashes. So the Southern Cross is a little bit higher. It's just around the Coalsack Nebula. But here is Eta Carina, and Eta Carina is the most amazing nebula that you can find in our galaxy. It is so exciting. And what I've done with the telescopes in order to really give you a view. Usually, when we do, it is possible. We have one telescope where we can take a color image of this beautiful nebula. Okay, so it's an emission nebula. It's very, very bright. But what I'm actually doing here is, instead of using a color filter on the other telescopes, on the bigger ones that give us more the narrow field, we're going to first get a map, a wide field, then we're going to narrow in, and then we're going to narrow in even more. That's why I'm running with 3 different telescopes, okay? One with a wide aperture is just taking different lenses. One with a wide aperture, then we get narrower and narrower to see all the fine details, okay? So really, really exciting. But what I'm doing here with the narrow ones, I'm not using normal color filters. I'm using so-called narrowband filters, and I'm using a so-called H-alpha filter. An H-alpha filter takes out the hydrogen emission line in the red, and we get a very, very fine line that way. And we can see details of the nebula much, much clearer. And that's exactly what all this is about. So I'm just going to see what our other friends are doing here. Let's see. One started successfully. Let's see what this one is doing. System status. Oh, they're all working away, which is good. We've got 3 telescopes working away. That's 13. Let's just see. We've got 13, 8. Yes, 8, 13, and 30 should be working. 30 is also running. System status. Let's just see. See where we are here. 1 second. Creating preview image. Okay, so this one's finished. That's great. I'm not going to show you this one first, because this is the big telescope with a very, very narrow view. I want to first show you the very wide view. So I'm just going to wait till this telescope is finished, which should be finished fairly soon. Okay, so we're going to take a wide view of Eta Carina. Now let me in the meantime just explain to you what Eta Carina is all about. It is definitely the jewel in the southern sky, and it spans over 300 light years. And what's interesting, we have in the north we have the wonderful Orion Nebula, which I think most of you must have heard about. Okay, so it's just ready. I'm just going to wait. It's just creating an image. And let's see if we can get this full screen. If we can do this yet. Just have to be a little bit patient sometimes. Wow, here we go. Isn't that beautiful? Now, this is really exciting because this is the most beautiful nebula that we know in our own Milky Way, the Eta Carina. It's, of course, again in the southern hemisphere. And what's exciting about it, this nebula, and let me just see if I can just get this. Yes, here's the information about this wonderful nebula. You can see it's in the constellation of Carina again. The distance is about 7,500 light years, so it's quite far. But what is amazing, it is bigger than the apparent size of our full moon, which is huge, and it's at a distance of 7,500 light years, and it's incredibly bright. You can actually really make it out as a fuzzy spot, as I just showed you before. Here you can actually see Eta Carina very easily, with the eye. So it is absolutely spectacular. So just before I'm going on, I must not forget to launch my last picture with. Before I do that, hang on, let me just see if the other ones. So this is the. Let's just go back in. Sorry, 1 second. Here we go. So let's talk about Eta Carina. So this is the wide field telescope, and what you can see here in the middle. I'm just going to get my cursor again. Right there is a very bright spot. You can probably see it. There, that bright spot stems from a huge mysterious star, which we now know actually consists of 2 stars. And this star is known as Eta Carina, one of the craziest stars that we know. So this is in the middle of this Eta Carina nebula, and it's huge. As I said, it spans over 300 light years right across. And right on top here, and I'm going to show you where my arrow goes, is another nebula, and that's going to be our final object, actually called the Gabriela mistral nebula. I'll explain that strange name in a while. So this nebula is really a birth center for stars. Lots and lots of stars are born here. This is actually an H-alpha picture. So we are just looking at hydrogen, at the hydrogen alpha distribution. So it's a very narrow picture, and it gives us the incredibly fine structure. What happens is around the star Eta Carina, which I'll explain in a moment, that is such a gigantic star, a lot of the gases are actually absorbed and simply burnt nearby, okay? So that causes also some of these rifts that you can see there. You can see some of the incredible rifts here, sort of black, gases just missing there, and then you can see enormous amounts of hydrogen gas, in different locations. So it's really interesting what's going on there. So let's just take a closer look now and see if the other telescopes are ready. 1 second. Where are we? Telescope, that was that. I need telescope number 13 now. That was 8. Here we are. Here's 13. Okay, here's 13. Let's look at the image. So we are now going to take a closer image, and this time it should be in color. Let's see if this is going to work. That's not quite the color image yet. I think the color processing takes a little bit of time. I just learned that earlier because this does appear in color. It will appear in color. So we may just have to wait a little bit longer because I had this before too. But this is a much closer look now of Eta Carina. Again, let me get my arrow. So this is all happening live. You see, that's the color processing takes a little bit of time, but that is our star Eta Carina. Now, what is so crazy about Eta Carina? Eta Carina is probably the most studied star in our galaxy because it is so crazy. It has a distance of 7,500 light years away, but, and now comes the but, it is about 5 million times brighter than our sun. Yes, 5 million. It's absolutely incredible. 5 million. One has to think about that. How is it possible? 5 million. And it actually consists of two stars. That's why it's not classified any longer as just a single star. It's a binary star consisting of two, but it's really complex. And it is called also an imposter for supernovas. Now, a supernova is the death of a star, of a big, large star, when it bursts out. And it's a final implosion and a massive explosion called a supernova. Now, this thing is a supernova imposter. It looked, and that was, I just had to see, I got notes here on the year. Yes, it was very interesting because between 1838 and 1858, this star suddenly became as bright as our very bright star Sirius. So it was the second brightest star in our galaxy, and it became so bright, and it weighs about 90 times our sun and is 5 million times bright. So it's a very, very young star, very, very violent. It is so massive that the gravitational force that is keeping the star together is hardly enough, because it is ejecting per year about 1,000th of the mass of our sun, which is massive. So it only has a short lifetime, and it seems to go through incredible cycles. And what is crazy about the star is it has this, what you call the homunculus nebula. The homunculus nebula is a nebula. It is sort of an explosive nebula. It looks a little bit like two dumbbells coming out of the center, and it is an enormous dust cloud traveling at incredible speeds away from the nebula. It is very, very hot. At the moment, the luminosity, that means the star is getting brighter, is increasing, and we don't know when this next violent eruption will be, but this star is wasting so much of its mass and throwing it out. It is very, very much studied. So really, really interesting. So much about that star. Now let's go and take a very close look, an even closer look at, let me just see, where is my T30? That should be it. Preview last image. Now let's just do this one. There we go, beautiful. Now this is incredible. So now we take an even closer look, and that is Eta Carina. That is this incredible star I was just talking, this supermassive star that has had these incredible outbursts and is increasing in luminosity all the time. What is also interesting is this whole region here, and this is again an H-alpha picture, which gives you the beautiful, beautiful fine details of this nebula, okay? We'll use a special filter for this, is you can see there are many, many young stars. All these are very, very young stars. With young stars, we mean stars that are 500,000, 1 million, 2 million, 3 million years old. So they're very, very young. And Eta Carina itself is also quite a young star, several million years old, but it's very difficult to study because it consists actually of two stars, as I said before. Okay. So what is also interesting is just nearby, and I have to just find it. It's approximately here, and it's approximately here, is a curious star, and it is even bigger than Eta Carina. No, is it bigger? I'm not sure, but it is similar in size. It's called a Wolf-Rayet. Those were a Wolf-Rayet star. Those were two French astronomers, Wolf-Rayet, or I think in English they say Rayet. It's a star that is an absolutely crazy star that is consuming itself and losing so much mass, also typical for a very big star. And I will actually show you a little bit more about this because now it's getting very, very exciting. Okay, so let's jump to an overview. This is an overview of the whole Eta Carina nebula, and this is a beautiful Hubble telescope picture. You can see it spans about 300 light years from left to right, and it is really such a heavy star forming region. Really, really exciting. So much going on. Very, very well studied. this was the picture that we just saw, and I'm going to just show you as a comparison. Now, emission nebula typically have a lot of hydrogen. So this is a picture of the hydrogen distribution of this nebula. It's a close-up that we just took with our telescope T30. Now, I have done yesterday, in a little moment just before the roof was going to open again, I have managed to take it also in different, at different wavelengths. And this here is this is actually the oxygen. Yeah, that should be the oxygen picture. So you have oxygen 3. This is doubly ionized oxygen. And you can see it looks very different. I'm just going to jump backwards and forwards. That's hydrogen. That's the oxygen line. The oxygen line is much more in the blue-green. And then you have another one called the sulfur filter. And so we have different filters. And then each time the nebula looks completely different. So what the Hubble telescope does, and what many others do, is they create a composite picture of these different ones. So again, we have hydrogen. This is you can see the oxygen distribution. There's a lot of oxygen around, and you can see all these young stars, by the way. It's quite beautiful, actually. The oxygen picture gives us a lot of details here. Look at all these young stars, and you can see Eta Carina again in the middle. Very, very nice. And then the final picture here is sulfur. And now the nice thing is, what happens if you combine all of these and try and replicate color with this? And Josep Drudis has actually done this job. It looks absolutely fantastic. This is Josep's picture image that he worked for, and this takes 30 to 40 hours of hard work to and I'm just going to walk a little bit through his image here. You can see how beautiful it is here, right at the edge, and it's such detail. So he's made this beautiful composition, and I think he won an award for this in his local astronomy club, which is the second biggest club, as I learned, in the whole world, in his region on the East Coast. And you can see the fine details. So what are we looking at here? Again, let me get my red arrow. Okay, here you go. This is Eta Carina, our crazy star I was just talking about. Now, what is interesting is the red corresponds to hydrogen. The very, very dark red corresponds to sulfur. And the blue, all the blue that you see, is more oxygen. So what you get is a beautiful, and he tried to make a realistic picture here of the nebula in its glorious, glorious colors. And he actually took the colors of the star in proper red, green, blue, and superimposed all these different colors, and you get this incredible detail of the nebula. It's just look at the incredible details. And what's interesting about this star is what is interesting about this star here, this is the Wolf-Rayet star I was talking about, a Wolf-Rayet star. Now, what on earth is a Wolf-Rayet star? A Wolf-Rayet star is another crazy massive star, and they're fairly rare. There are about 500 such stars in our own Milky Way, and they're super massive. Again, you're talking about a luminosity about 1 million to 2 million times our sun. Very young stars, and they're consuming hydrogen at such an incredible rate. And they also have, in their shells, they're consuming helium now, right to the core, iron, so oxygen, nitrogen, they're going through the whole cycle, shell by shell, at an incredible rate. Very, very bright stars, very interesting stars, and I do hope that one day I will be able, because there is actually a Wolf-Rayet star in the southern hemisphere that we can look at and do some emission line spectra on that. And what's beautiful for people is this all happens in the visible region, which is so wonderful. This is the region we're looking at, and we can do all these wonderful examinations of Wolf-Rayet stars or similar stars. We take the spectrum and we can do that. And I hope to show you that live one day. So I think this sort of concludes my quick explanation of our wonderful Eta Carina nebula. Okay, and let's go to our final object. And that, I'm just going to jump back to our live screen now. Here we go. Get rid of my arrow. So far my system hasn't crashed, which makes me very happy. Let me see, where are we here? Is this the one? Let me see if this was the one plan. Is this T30? Let me just see what the picture looks like. Preview last image. Let's just do that. See what we get here. Because this is the final nebula we're going to look at today. Well, it's taking a little bit time here, so let's just wait. It's doing something, maybe it's just creating the image as we speak. Let me just check quickly. T8. You know what we can do in the meantime? We can look at T13 again and see if the color image is now available. Wait, that was T8, T13, preview last image, because we are still missing the color image. It still doesn't look color. Looks like a color image. I have though seen it. Usually it's processed in color, so that is missing today. I'm not quite sure what the reason is, but this is usually in color, if I see this correctly. Yes, it is usually in color. Don't know, maybe it takes a little bit of time still. So let's just see. So by the way, the Gabriela Mistral nebula is the one we're going to look in detail. That was the map we did of the beautiful Eta Carina nebula, and the one here in the northwest, it's the northwest corner actually of the nebula, is the one we're going to look at right now, which is also really curious. So let's see, where are T30 was, 1 second, T30. Has it taken it now? 1 second, let me just see. I have to remember now, did I take this now or did I not? Let me just see. Let's preview the image. There we go, let's just have a look. Okay, I may have just forgotten to take it, hang on. I think what I did is I have not taken our final image yet, as it seems to me. So let's just jump back again. T8, okay, let's do it again, doesn't matter. It's okay, NGC3324, get the coordinates, and we'll do it quickly. It's fine. There we go, let's acquire the image. I may have forgotten that, I'm not sure. I'm parallel processing a lot here. So again, what are we doing here? We're taking an H alpha, which is the emission line of the nebula, and it's really, really wonderful to look at this one because I'll give you a little bit of the history in the meantime, whilst it takes the image. Maybe I'll show you some results in the meantime, so we can save a little bit of time, okay, of the whilst it's doing this. So let's just jump ahead, because just in case, let's see. So this was all Eta Carina that we saw. We saw a beautiful M, and this is now going to the Gabriela Mistral nebula. Now, why is it called Gabriela Mistral? That is an interesting question. Well, it's about this nebula is another emission nebula, and it's a very, very rich hydrogen, an ionized hydrogen region, and there's also an open cluster there. Let's see if we can see the open cluster. 1 second. In our wide field picture there, yes, I think we did see the open cluster. We did actually. So, what is interesting about this is it is surrounded by intense ultraviolet radiation. These are very, very important hot young stars that are actually exciting the cloud, and the stars are eroding away a lot of the nebula itself. And what is interesting, why is it called Gabriela Mistral? Well, Gabriela Mistral is or was a Nobel Prize winning poet from Chile. And what is interesting about the profile, and I'm going to show you this right now, this is the result. Look at this profile. If you look at the nebula, and again, this is thanks to Josep Drudis, who did this incredible combined image. If you look at the profile of this nebula, it very, very much matches her. So she is a very, very famous educator in Chile, and she did a lot for education. She wrote incredible poems, and she got a Nobel Prize. I don't remember the exact year that it was, but I do remember that it was, I think she was born in the late 1800s something, and I think she received a Nobel Prize in the early 1900s. Really, really beautiful work of hers, and some incredibly creative person actually saw the similarity of her Nobel Prize winning picture, and that is where this nebula got its name from, Gabriela Mistral. Really beautiful, really, really beautiful. How difficult to assign color to each filter, asked Bart. Hi Bart. Sorry if I missed your comments. Please go ahead with comments. How difficult is it to assign colors? It's very, very easy on a telescope. Let me just do this quickly for you. And let's see if I'm answering your question, okay? So let's assume you want to do an image. And I'm going to jump to another telescope now. Let's just do that. Telescope 8, yes. There we go. Let's say you want to do a single image, okay? No, let's do an image series. Sorry, an image series. Here we are. So you just click, I want to run an image series. And you can choose that. So all you do is type your target. Well, you name the target, Bart. What target would you like? Let's say, well, let's just write something. What is an interesting target at the moment? Well, maybe we'll just take Omega Centauri like we did before. Okay, so you would just press let's get the coordinates, and you get the coordinates there, and it tells you that, gives you the coordinates visible, and all you do is put the filters in. Typically we use 300 seconds, okay? So let's say you want to do a red, green, blue. So would do the first one red. 300 seconds is a very, very good time to use. And then you can use the number of images. Let's say you want to make a very deep one. So initially you would use 5 reds, and you would use binning 1. Now what on earth is binning? Binning is something we don't have with normal cameras, okay? Binning is something that we have for astronomical cameras. What you actually do is, instead of using 1 pixel that catches light, you take 2 by 2 pixels, and we call that binning. So you take 4 pixels together and you make it into a super pixel, a super sensitive pixel that can gather 4 times as much light. So, but you are losing resolution through that. Okay, so that's why we bin. Binning is very good when you to use often with narrowband filters. So we would use red, and I would make it 5. Let's do the next one, blue. And I would do it again, binning 1, and make it 300 seconds. Don't forget, there's always seconds, right? And then we would do another 5 here, and we would use green. There you go, and we'll put 300 seconds there, do binning 1. And then you can do more. Luminance is also important. Luminance gives you the overall picture in white, okay? So that you would use what you call an LRGB image. Luminance, red, green, blue. And then you would process all that image together with software such as CCD Stack, such as MaximDL, such as Pixel Insight, and so on. There are different softwares you can use for this. And if there's interest, I can definitely in future give some lessons on that. Now, if you want to do some narrowband too, you can just go on. Well, I'm going to add another one. I want another 5, and because narrowband is narrow, so there's much less light, I'm going to do binning 2 here. So that gathers 4 times as much light, but you lose in resolution. But you don't need the resolution maybe for the picture that you use. And then you have all the options, then you just press acquire image and off you go, end of the story. Really simple, really, really simple. Now, if you don't want to do all that, you can just click on the one-click image, but that wasn't your question. Your question was how difficult to assign color. So that hopefully, Bart, gives an answer to your question, okay? So let's jump back now and let's see how far we've come with our Gabriela Mistral. Hopefully it's finished now. No, have I not taken it? That's strange. I'm not sure what it is at the moment. 1 second. Let me see. Oh, it's still taking it. I'm sorry, it's still taking it, okay? It's still in the process of taking it. So I will jump back, and if you have any more questions, please throw them in. I'm very, very happy to see your questions. That's what it's all about. It's going to be very, very interactive, okay? So in the meantime, as we take the live picture, I just want to jump back and explain a little bit about the Gabriela Mistral. So this is actually how it's going to come out, and that's why I'm doing it live also, that you can see this. But it's an incredible nebula because it's very, very dense. As I said, it's has a lot of ultraviolet light, and this is the hydrogen image of that. Okay, so this is the hydrogen picture. So you can see how incredibly detailed the hydrogen picture is. Now again, you can take the different narrowband images, which is very interesting to do with nebula. And this, for example, is the oxygen. So compare the oxygen here with the hydrogen. You see that? That's the hydrogen emission. That's the doubly ionized oxygen. And that is the sulfur picture. Isn't that interesting? So you get all these different layers, and with these different layers you can make a composite, what we call a false color image. A false color image. But if you do it like our friend Josep Drudis, and by the way, I have given his incredible website details, and I acknowledge the permission here that we can use his pictures because they're really, really incredible. You can see how beautiful this Gabriela Mistral nebula is. The blue again represents oxygen. Mainly, so he's done a false composite here to sort of make it look realistic. Okay, so that's the blue as the oxygen. Then you have this incredibly deep red. And if you remember the sulfur, this is actually the sulfur picture. That's the sulfur, okay? That's the deep red corresponds to sulfur, and the lighter red regions are all hydrogen, okay? Now look at the hydrogen picture. That's just upside down. That's the hydrogen picture that we are about to take, saving us a little bit of time now. Let me get the arrow out of the way, and hopefully we have it now. Preview. I can prove to you. Yes, there we are. Isn't that beautiful? That's our hydrogen picture. Now we have it. So that's the hydrogen alpha line, and it looks. You can see it's on its head. It's just like I promised it would be, and you can see this. You can see her. The shape of her whole head only upside down. Okay, so if you do, so that really concludes the image taking for today. So just to finally conclude our session, it's been a bit longer today because there was so many beautiful things to explain. Again, that's the here you can see the incredible beauty of the Gabriela Mistral image. I'm just going to move a little bit through it so you can see that. As Josep has shown this and taken this, and it's taken, this is taken, again, I think 20-30 hours of imaging to get that to that level of detail. But you can see the more you can go incredibly deep with this. Okay, and there again is the comparison of the nebula with this incredible poet. And that sort of concludes the session for today. And I sincerely hope you enjoyed this. Don't forget to subscribe. We're going to make the whole of February free. Now, I'm going to go on holiday on Thursday, and I will try, if possible, to do some live sessions. Now, YouTube doesn't yet provide the ability to do mobile sessions yet, but since I need so much equipment, I'm going to do another session, and hopefully it'll be fine. My final session before I go on holiday will be on Wednesday evening, and it's also going to be free. It's going to be about the wonderful Sombrero Galaxy and the Black Eye Galaxy. Very exciting. So do join me. We're going to talk a lot more about galaxies there. And there is so much to explore in the southern sky, so I do hope you find it exciting. If you do miss it, it doesn't matter either. You can go and have all the replay, but be sure that you join the session. Be sure that you comment. All your comments are very welcome. This is very interactive. It's very different to the normal webinars. Webinars are not episodes. And it would be very, very good to have a lot of you participating, commenting, and this will make our sessions more and more interesting. But we have incredible possibilities here at the Southern Sky, and we're doing all this from the Northern Sky, and it's a wonderful way to interactively educate ourselves and explore astronomy. So on that note, join us for episode 3. We will release images very shortly. I will compile them today. We've got a bit of things to do this morning, but I'll compile them in the afternoon and make them available. I will put the link out again. Let me just go back to the links. Let me just show you that. So usually they will be, oops, sorry, I have not, I'm still, let me just clear the picture here, 1 second. There we go, now you can see it, now you can see it. So usually all the information of each episode, together with the download link, is provided. So on episode 2, I will then in a few hours give you the download link, and I think we'll also include it in our newsletter, so where to go. So do make sure that A, you have a YouTube account, that you can comment. B, you tell your friends if you like what I'm doing or like what we are doing. I mean, it's a whole team that's working at this to make sure. And sometimes we are very, very weather dependent, but we'd love to have you here. And I think you'll see it's a lot of passion and enthusiasm here at iTelescope. And there are many, many ways to explore. We can explore the planets, which we will do. We'll explore distant galaxies. We'll explore the Milky Way in detail, all the emission nebulas, globular clusters, open clusters, and so on and so on. So lots of things to do. We can look into star spectra. We'll look into Jupiter and Saturn soon, and so on and so on. So even if there's full moon, there's always a lot of wonderful things to do. Okay, well, having said that, thank you for joining. And if you haven't seen it, there's always the replay. So on that note, all the best. And I'll see you very soon.